Right, so many physical quantities such as speed, just reading straight from the box, guys, can be completely described as a single number called a scalar. And a scalar is really about the size of a quantity, like how fast you're moving is a scalar. And the number indicates the magnitude. Ooh. So what a vector is right here in this blank, a quantity that is both scalar with direction. So that right there, that's going to be kind of the key flag that we're dealing with a vector and not just a scalar quantity. So we're going to look at just some actual conceptual examples, and the rest, like I said, is pretty abstract. All right, here we go. State whether each quantity is described as a vector or if it's just scalar. Vector is so easy because it's going to have direction. On number one, we know a boat is traveling at 15 miles per hour, but we have no idea which direction it's going. So this is scalar. Number two, a hiker is walking 25 paces due west. There's our little flag there. We know this is a vector. A person's weight on a scale, you can't really have direction on that, so that's going to be scalar. And then a parachutist falling straight down, that's a direction. Up, down, left, right, those are directions. So this is also a vector. Anytime you know which way a person's heading, it's probably going to be a vector. So, a vector, remember it combines direction and a scalar quantity. We can write a vector in component form. And component form is like the end from the origin. Like the end product, the final product. You know you're always looking at a vector in component form when you see those pointy grouping symbols. Y'all, we treat it like an ordered pair, but it is a vector, and we are going to use this symbol. Speaking of symbols, a vector can be written like that, or it can be just written as vector V without that little tail, like half of an arrow. Okay, so here's how we're going to find component form. Let's say we have an initial point right here, and we have an end point up there. We're just going to subtract these amounts, and that's where it's going to be relative to the origin. So you can consider these to be like endpoints of a line segment. But the order matters. So it is always the terminal minus the initial. Notice they both have 2's right here. Terminal minus the initial. All right, here we go. Let's just do some examples on this beautiful concept. Find the component form of the given vector with the following initial and terminal points, then sketch the vector in standard position. All right, we know that it's going to start at -4, +2. We know it ends at -3, -5. We're going to do it in standard position from the origin. Let's find the vector form. So remember, it is going to be terminal x minus initial y. So terminal x minus initial y, that's going to turn into a +7. That's the first x value for component form. Terminal y, which is -5, minus initial y, which is 2. That's going to be a -7. So component form, guys, where this ends up being on a coordinate grid, it is, I meant to write the letter B there. AB is going to be at +7, -7. That's where it ends up being on a coordinate grid, at that exact point. All right, let's find component form for CD. So end value for the x is -9 minus the beginning value, which is 0. -9 minus 0 is just -9. Now let's look at the y's. -3 minus a +8. That's going to be a -11. So component form for vector CD is going to be -9, -11. So you can have 2 points anywhere on the graph, like in random spots, but component form is always relative to the origin, and it shows where it ends up being based on an ordered pair. All right, we have like 6 things to knock out. We just knocked out the first one. The second one is not too bad. It's just the different ways that you can write a vector. All right, so unit vectors. Unit vectors are like unit rates, like from Algebra 1. So if you notice, we'll look at this first, then we'll put it all together. I have a vector I. Vector I only moved one little baby spot to the right of the origin. It didn't go up or down at all. That's the unit vector for horizontal movement. Letter J, kind of the same thing, but it didn't go horizontal. It just went up one. So what we're going to do is we are going to break up component form and rewrite them relative to letters I, which is sideways movement, and letters J, which is up and down movement, vertical movement. So here's your little graphic for component form. All you do is put these numbers in front of I and J, and boom, that's linear combination form. All right, so let's go ahead and find component form. Then we're going to rewrite it in linear combination form. Here we go. I don't really have any name to call this vector, so I'm just going to use kind of the generic name. Just like X is the generic unknown, V is like the generic form to name a vector. All right, so we know it ended up at 3, but it started out at 0. So 3 minus 0 is going to be a 3. And then it ended up at +6, but it started out at -2. So 6 minus a -2, that's going to turn into a +8. Remember the whole negative thing. So that's component form, so easy to write in linear combination form. It is going to be 3i plus 8j. That's it. All right, let's try it again. Let's look at this next one. All right, plain vector v, component form first. I ended at 0, but I started at -6. So 0 minus a -6, that's going to turn into a +6. And this is going to be 1 minus 4 for the y value, so that's going to be a -3. Component form, knocked it out. Linear combo form. Guys, make sure you write a minus in the middle because the 3 was negative in component form. So if it's negative, you do need to write a minus sign there. And that's it. That is linear combination form.